So the title for this section of the lesson is Newton's Law of Cooling, which is a specific application of a differential equation. And to be honest, for as much as this lesson is all focused on this thing called Newton's Law of Cooling, in some sense it's not about Newton's Law of Cooling. On the AP exam, they're not going to require you to have memorized this. They're not going to test like, oh, did you memorize Newton's Law of Cooling? What they want to know is, can you understand a new differential equation when one is presented to you? And Newton's Law of Cooling is one way of us looking at a differential equation. So I'm going to get into Newton's Law of Cooling here, but please don't be focused on memorizing Newton's Law of Cooling as much as on understanding how we're solving the problem. So let's get to the problem. So Newton's Law of Cooling actually states, as I say here, that the rate of change of the temperature of an object with respect to time is directly proportional to the difference between the temperature of the object and the constant temperature of the surrounding medium. So based on the lesson that you guys saw yesterday and or the day before that, you should be able to take this thing and write a differential equation using the variables t, little t, and the constants big M, and maybe some constant of proportionality called k. So I'd recommend you pause the video and see if you can write the differential equation that this sentence is indicating using those letters. So I hope you tried that on your own. It says that the rate of change of the temperature of an object with respect to time, so that means dt is directly proportional to equals k times the difference between the temperature of the object and the constant temperature of the surrounding medium. Well, the temperature of the object is big T, the temperature of the surrounding medium is M, right? So that's the differential equation that goes with this statement, that goes with Newton's Law of Cooling. Right? Newton's Law of Cooling is effectively this differential equation. Now what I'd like us to be able to do is I'd like us to be able to solve this differential equation. And again, when I say solve this differential equation, I don't necessarily just mean Newton's Law of Cooling. Please don't feel like, oh, this problem is definitely going to be on the test. I'm going to want you to be able to solve some differential equation, right? So solving this differential equation, our first step is to multiply the d little t to the other side. So this is dt equals k times t minus m dt, right? Now I actually want to separate variables. Remember, my variables are capital T and lowercase t. K and m are both constants, right? So what am I going to have to do to separate big T and little t? Well, there's a big T right here and it's connected to the m, so I think I'm going to have to divide that thing over. I'm going to end up with dt over t minus m equals k d little t. So now I've separated variables. My next step is to take the antiderivative of both sides. And based on some of the discussions I had in class yesterday, I think, for as much as I'm going to take the integral of both sides, I think it's going to be helpful if I sort of rewrite the one on the left. Remember that when that dt is on top, we can actually write it next to the problem and just have this. So the integral 1 over t minus m dt equals, and on the right side, that should be a pretty easy integral. If I'm doing the integral of a constant k with respect to little t, this will be k little t plus c. Now, this integral on the left is a little bit complicated because it's not just 1 over t, it's actually 1 over t minus m. So I may need to do a little u substitution. I'm going to do that over on the side. If I have to do the integral of 1 over t minus m dt, I'll make my u the thing on the bottom. Oops, sorry, just realized that should be a d big T. So let's see here. I should have t minus m. So what is du? Well, the derivative of t is dt. The derivative of m is basically 0. So it's du equals dt. So this integral is just going to transform into the integral of 1 over u du. And so I'm going to end up with the natural log of u. And remember that then we plug our u back in. So the left side is going to be the natural log of t minus m. I know this is complicated because there's just letters everywhere, but look at that and make sure that you're comfortable with that. Pause and go back if you need to. So the left side is the natural log of t minus m equals kt plus c. And this is where that trick from yesterday is going to come in. When we've got a natural log on the left, remember we can exponentiate. So I'm going to go e to the kt plus c equals t minus m. Right? Then remember we did that trick yesterday. You can rewrite this left side as e to the kt times e to the c equals t minus m. But remember that this e to the c is just some other constant c. So I've got ce to the kt. And so at the moment this is looking really similar to what we did yesterday. The only difference is if I'm going to solve for t, I've got this m to deal with. All I have to do is add that over. The temperature of the object will be ce to the kt plus m. This here is the general solution for Newton's law of cooling. Again, mentioning it for about the 10th time in this video, the purpose of this is not for you to memorize, oh cool, that's Newton's law of cooling. The purpose of this video is to talk to you about this process, about us taking a differential equation, taking some statement of some law, writing a differential equation for it, solving that differential equation, and getting a solution that can be applied to a problem. I do have an example of this problem, like in use, us actually using this, and so I'm going to go into that now. Sorry this video is a little on the long side. I'm hoping I can keep the second one a little bit shorter for us. But there's only 2 videos tonight, so you'll survive. Okay, so my example, right? I've got an object that's 1,000 degrees, so that's sort of the temperature of the object that's going to be changing, and it's dropped into this large vat of water that's held at a constant temperature of 80 degrees, right? So that's the temperature of the medium. The temperature of the object falls to 900 degrees after 3 minutes. Part A, I want us to write a function for the temperature of the object as a function of time. So from the previous page, we know that the temperature is going to be ce to the kt plus m. Do we know any of these constants? There's actually 3 constants. There's c, k, and m. Right? We do know one of them. We know that the temperature of the surrounding medium is 80 degrees, right? So I can already refine my equation to ce to the kt plus 80, right? In order to find c and k, I'm going to have to use other information from the problem. In particular, we're told that the temperature of the object is initially 1,000. Which means the temperature is 1,000 when time is 0. So that means I'll have 1,000 equals ce to the 0 plus 80. If I subtract the 80 over in short, I'll find out that c has to be 920. Right? So I refine my equation. Right? My equation has one fewer constant in it now. It's now t equals 920 e to the kt plus 80. Now I'd love to figure out what this constant k is. So fortunately, we're told that the temperature has dropped to 900 after 3 minutes when when little t is 3. So I'll plug that in, right? I'll say, okay, 900 is equal to 920 e to the kt k times 3 plus 80. Right? Now I'm going to sort of skip some steps here to save time. I'm going to subtract the 80 over, and then I'm going to divide by 920. That'll give me 820 over 920 equals e to the 3k. Then to solve for k, I'm going to do that natural log business. So I'm going to get 3k is equal to the natural log of 820 over 920. And again, I'm assuming we can do the arithmetic here in the calculator usage. You do that natural log, you divide by 3, you'll find out that k is going to be negative 0.0384. And as I mentioned in the previous video, please, please, please store this, right? Store it to k on your calculator. But long story short, you've got the temperature of the object is 920 e to the negative 0.0384 k plus 80. That's the answer for part A of the problem, right? Part B, they're asking, what's the temperature of the object after 9, was it minutes? Yeah, after 9 minutes. Right? Oops, I just realized that I made a mistake there. That K, and I don't think I can erase it at this point, that K should have been a T. That was time there, not K. So for part B, if you want to know what the temperature of the object is after 9 minutes, simply plug in 9 for T and use your calculator. I'm not even going to show steps here to save time. The temperature of the object at this point will be 651.427 degrees. Question C is asking when, so it's asking for the time, at what time the temperature of the object will be 500. Great, so we plug in temperature being 500. If I plug that in, I'll have 500 equals 920 e to the negative 0.0384 t plus 80. And again here, I really feel like I should be able to skip some steps here. I'm going to subtract 80, divide by 920. We'll end up with 420 over 920 equals e to the negative 0.0384 t. Again, we're going to do the natural log trick, and you'll have to divide by this. The time at which this happens is going to be 20.443 minutes. So after, about 20 and a half minutes, we'll reach this temperature. And then the last question, part D, and this is a pretty important conceptual question. It says, how long will it take for the object to reach 50 degrees? So we have to plug in 50 for T. If I plug that in, I'm going to end up with 50 equals 920 e to the negative 0.0384 t plus 80. And I know I'm moving fast here, but I know I'm way over my time on this video, so I'm trying to go quick. Long story short, if you subtract the 80 and divide, you're going to end up with negative 30 over 920 equals e to this power. Your next step is to try and take the natural log, but when you try to take the natural log of a negative number, it blows up. And the question is why? Why is it that this doesn't work? And it makes sense. If you drop something into water that's being held at a constant temperature of 80 degrees, there's no way the thing's going to become 50 degrees. It will drop from 1,000 degrees down to 80 degrees and then not below that. So getting to 50 degrees doesn't make any sense at all. This was a very long video. And all of it is this very extended example of Newton's law of cooling. Remember, this problem is a lot less about Newton's law of cooling and more about our ability to deal with any differential equation that we encounter. So hopefully that makes sense. The second video will be a lot shorter, and that'll be it for today.